Okay, let's talk about absolute and conditional convergence. And in this lesson, I'm not going to talk about the ratio test. So if you're looking for ratio test examples, you won't see that here. And if you want to print the guided notes sheet, you can go to this bit.ly link down here. It is case sensitive. Abscond, it's also a word, abscond. Isn't that neat? Like I did absolute and conditional, but I spelled a real word. Ha! All right. So let's talk about absolute and conditional convergence. Saying something converges absolutely is not a statement of confidence. It doesn't mean that you're really sure of the answer. It has a very specific meaning. And absolute convergence means that your series converges and its absolute value converges. So if the original series and its absolute value converges, we call that absolutely conditional, absolutely convergent. However, conditional convergence is when your original series converges, but when you take the absolute value of it, the absolute value of the series will diverge. So we call that conditional convergence because it only converges on the condition that you don't change it, that you leave it as is, and that's going to be typically with alternating series. And then lastly, do remember that if the absolute value of a series converges, then so will the original series. So that's just a good little tidbit to use. And let's look at a few examples. That is it for the notes. Let's just do some examples now. So we're determining whether these series are absolutely convergent, conditionally, or divergent. And so this first one, I always, every time I do convergence of a series, I will always consider the absolute value of that series first. And so if I take the absolute value of this series, it results in just 1 over n squared. And that's a pretty nice series, isn't it? Because I recognize that as a p series. P is 2. 2 is indeed greater than 1. Therefore, the absolute value of my series converges, right? Which means that my original series, negative 1 to the n over 2n squared, that means this series is absolutely convergent. I'm spending more time writing than I'm talking. Okay, so that one was pretty nice. If the absolute value of your series converges, then your series is absolutely convergent. Onward. Okay, so let's try this one. So again, I'm going to start by considering the absolute value of the series. And when I absolute value this guy, we end up with a series of 1 over the square root of n. That is, again, a p series. This time, however, p is 1/2. That is less than 1. Therefore, the absolute value of my sequence, or series, if we call that a sub n, the absolute value diverges, which means we now need to go back to the original series and consider it as it originally was presented. And this original series is an alternating series. So I'm going to kind of recreate it down here. And this is alternating. With my sequence a sub n being 1 over the square root of n. And an alternating series will converge if your terms approach 0 and they decrease. And so I have a 2-part test here to finish this. I'll just bullet them. So first, I'm going to consider the infinite limit, the limit as n approaches infinity of 1 over the square root of n. And that does indeed equal 0. We're bottom heavy there. And I also need to know that the series decreases. So is the n plus first term, 1 over n plus 1, is that less than 1 over the square root of n? And that is a larger denominator. A larger denominator favors a smaller fraction. Therefore, a sub n decreases. And we do indeed meet both of the conditions for the alternating series test. That means my final conclusion is, man, my writing is sloppy today. I think it's because it's Friday. That's what it is. It is for me anyway. Not sure where you are. All right, so negative 1 to the n over the square root of n. That series, it converges, but its absolute value diverged. Therefore, this is conditionally convergent. 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 There we go. Cool. So we see the difference between absolute and conditional. Let's look at the next one. 1 over n ln n. And this is a neat one because this one does not alternate, which means if you take the absolute value of the series, this series is already positive. So the absolute value of that series is just going to result in the original series. So if this guy converges, if this does indeed converge, then this series will be absolutely convergent. So we have the absolute value. I took a little break there for a second. I got to get my brain back in line here. Natural log of n. Okay, so absolute values do not come into play here because the series is already positive to begin with. And so we need to determine if this is convergent. You may want to consider a direct comparison first to the harmonic series. Unfortunately, we are less than a known divergent, which is inconclusive. And this guy actually relies on the integral test to prove whether this converges or diverges. And for the integral test, you want to consider the function f of x that is the same formula as the sequence. So 1 over x times the natural log of x. And we want to see if the improper integral, in this case it's from 2 to infinity, of 1 over x ln x, if that converges or diverges, and the series will have the same behavior as the improper integral. Now for the integral test, you do want to confirm that your series is positive, which this one is, we've already talked about that, is continuous, and 1 over x ln x is continuous for all x is greater than 2. And we want to make sure this is decreasing, and if you plug in n plus 1 for n, you will see that the n plus first term is always less than the nth term. So we do meet the conditions to apply the integral test, and do remember that when you're doing improper integrals, you want to start by converting your improper integral to a limit. So we're going to limit as a goes to infinity of 2 to a of 1 over x ln x. And I'm going to pause this while I work out the antiderivative just to cut down on some length of the video. And I'll be right back as soon as I have the antiderivative worked out. Okay, so I found the antiderivative. This is a u sub. The antiderivative ends up being the natural log of x, some natural logception there. And as a goes to infinity, bring back the limit. As a goes to infinity, this guy right here, the natural log of infinity, that guy is blowing up. This is a constant, which means this limit does not exist. And if the limit does not exist, that means that my series will diverge. And so we have 1 over n natural log of n diverges. And divergence is just divergence. There is no such thing as absolute or conditional divergence. So we do have absolute and conditional convergence. But when it comes to divergent, you just diverge. And that's your answer for that one. So good old integral test. This is my least favorite one. All right, let's see. Last one. And this one is alternating. So this time the absolute value will come into play because it will change possibly the behavior of this guy. Well, not the behavior. I said that wrong. Whatever. Still doing the absolute value. And when you absolute value that, you end up with just the inverse tangent. Actually, it's the absolute value of the inverse tangent of n, because inverse tangent could be infinity. Could be infinity. Could be negative. And the cool thing I know about inverse tangent is always less than pi over 2. If you graph y equals inverse tangent x, there will be a horizontal asymptote at pi over 2 that function approaches. And so this series will always be less than pi over 2 over n factorial. And that, guys, this guy is a very strongly convergent series. A constant over n factorial, you could show fairly easily that that is also less than 1 over n squared. N factorial will beat the pants off of n squared. That converges. And so if I follow my chain of inequalities, this guy converges because that was less than the known p series that converges, which means my original series, the absolute value of arc 10 over n, that converges. And if the absolute value of the original series converges, then the original series converges. And so I'm all the way back to this original guy. Therefore, the absolute value of this converged. This is absolutely convergent. And again, that is not a statement of confidence. Absolutely convergent is not saying that I know it converges. It's saying that the series and its absolute value converges. So there's some examples of absolutes and conditional convergence, and hopefully that made some sense to you.